So for the benefit of James, we're going to just quickly pick up from where we left off last class, because what we were discussing was an issue that was a major problem in the 1700s, or at least it's been a problem for a very long time, but it became important in the 1700s. I'll explain why in a moment. We are looking at how do we determine where we are on the surface of the Earth, to then translate that into how we might determine where we are when we are flying an aeroplane. So I roughly started to highlight towards the end of the class what those lines mean. Now you know from your geography classes that the ones running around are the latitudes and the ones running from pole to pole are the longitudes. Latitude is reasonably easy to determine because the sun gives it away. The position of the sun, angular position of the sun, which can be determined most times of the day, but certainly in midday and on any particular day, is going to tell you how far north or south you are of the equator. Now you know that the Earth tilts, so you also have to have in mind what time of year it is. So at certain times of the year, the sun is going to be further north in the southern hemisphere and further south in the northern hemisphere, so to speak, you know, whichever period of time it is, winter, summer. But that's not too hard to know because that happens every year. So over a period of time, people recognize the patterns. So that pattern of where the sun is not particularly hard to determine. One of the tools that was used for that was just an angle that you'd place up to the sun at a certain time of the day. So if you looked at it at lunchtime or middle of the day, you knew where the sun was, you could determine pretty much how far north or south you were by that angle. That would later be determined into the sextant type arrangement you see in the movies where they've got a little telescope and they look up and see where the sun is and place it half, and you know, there's a little bit more going on than that. The big problem was knowing where you were east or west. Knowing north and south wasn't too hard. East and west was where it was a problem. So towards the end of the 1600s, they were starting then well, there was Christian Huygens, a couple of other scientists of the time were Thomas Hooke rather, were looking into how to make springs that would actually work backwards and forwards in a determined way, predictably determined repeating patterns. That's what you need when you want to make a clock. And so clockmaking became fairly precise in this period, the late 1600s, late 1700s, 16th century. So you then start to enter into the next century, and naval power was becoming important for big countries like England, France, Spain, and being able to move around the world and not run into things in the night time. So knowing where you were was very important. So there was a commission put up by Queen Anne, I think it was, 24 guys to get together in the scientific community and from business communities and from the maritime communities, working with the Admiralty to come up with a way of finding your time while you're at sea so you could then work out where you were in terms of longitude. And they put forward a competition. And that competition had some pretty good prize money involved. In today's money, the award for they had a different rankings. They said if you could find your longitude to within 60 kilometers, you'd get a certain amount of money. If you could find it, well, not 60 nautical miles, and then 20 nautical miles was the one they were really after. Now 20 nautical miles today sounds like that's ridiculous. Your GPS can pinpoint your car to within 5 meters or so. They were going to give you this money if you could work out where you were in longitude to within 20 nautical miles. And that's a fairly large distance to miss on. But they were pretty convinced that that would do it. £2.5 million was up for grabs. In our days, in our day money. You know, it was like £5,000 or something to them, but in our money it was £2.5 million. It was that was so important. And a fellow named John Harrison put together a clock that would work. It became the marine chronometer. Now, he borrowed money from the Admiralty to build this thing, so they paid him something. And when he finally got it done, the commission reneged on the payment because apparently they said he was working for them and such like. So, you know, so he never got his £2.5 million. But he is regarded as the man who came up with the clock that we currently consider to be the kind of timepiece we need for accurate navigation. He's listed as, I think, about the 30th or 39th or 40th most famous Brits that no one knows. You know, so he's pretty high on those famous Brits that no one knows. Now, why is it that longitude can be determined by time? Well, you've heard of Greenwich, you know, right? Greenwich Mean Time. Now, if that line that I've got there on the Earth's surface is considered as a starting datum point. So you're in a boat, you're leaving Britain, and you're able to see because they put it on the top of a tower and they put this big ball on the top of it, and every hour they lower the ball so you knew what time it was, and you could see that from out at sea because you've got a telescope and you could look at Greenwich and look at the timepieces that were available. We had one here at the observatory, so that the same thing was allowed in the 1800s. That ships would come in the observatory in Sydney on Observatory Hill. One of the jobs it had was to provide a time register, so you knew what time it was. Anyway, bottom line is this. You get your clock and you set it to the time that you are leaving Greenwich. And then you know that this time in England is 6 o'clock. And you sail west. Not much to sail east from Greenwich because you run into France. But so you sail east and you head out into the Atlantic. Now you need 2 more pieces of information to get really accurate positioning. I'll get to the second piece of information in a moment. But if the next day you wake up and you look at where the sun gets up and you wait for the sun to break the horizon and you look at your timepiece and you find out that the sun has gotten up an hour later than what it would have gotten up if or had sunrise in England. So you know now that you are 1/24th of the timepiece around the planet. That gives you a position of longitude. And more of it does, an hour makes it nice and easy and round figures to work with, but it could be any time frame. So it could be minutes that you're different. Now you know how far to the east you've gone. Same applies to the west. Same applies going to the east. How early the sun gets up compared to Greenwich Mean Time, to 0. Once you've got a clock, you can do this. And that makes it really easy to work out where you are. Now, the reason this came up was that there was a disaster off the coast of Sicily where a part of the Admiralty's fleet, 4 ships in the night, sailed straight into the islands, the rocks around Sicily, and people were killed. And the reason they got it wrong was they didn't know where they were in longitude, and so they hadn't made the manoeuvre to turn at the right time, and they delayed the turn and ran into the islands. So that was basically the impetus for the creation of this concept of finding east and west. There was a second thing you needed. What do you think the second thing you needed was? So you now got 2 big ingredients for timing where you are. You can pick out your latitude from the sun. You now have a longitude because you worked it out from the time and the risen sun or the position of the sun at certain times. What's the next thing? Speed. If you don't know your speed, then you can't work out how far you might travel or could have travelled in that time frame. Right, so speed becomes important. So speed was handled how? How did ships determine speed? In knots. What's a knot?
It's a knot a metre away from each other.
Pretty much it's a length of rope with a knot in it, yeah. And you throw this over the back with a particular piece of wood at the end which will drag in the water to a known degree. So once you've got that and you throw that into the water, you know, and you sit there with your timepiece and you count the knots going over in a certain time frame. And because they're all known lengths, you can multiply those known lengths up to nautical distances, so miles, and so you can work out from in a 10-second or 15-second a lot of knots going over. That's how fast your boat is going. So that then gives you the 3 ingredients you know to find out where you are at any given time. 2 cool things about that. One guy who became really, really good at this sort of stuff in the late 1700s, he was then given jobs that he had 2 skills that were fantastic. One, he was a fantastic cartographer. That's a person who can draw really good close maps, and very accurate. But he was also a very, very good dead reckoning navigator, and that's James Cook. And so he was elevated to do exploratory work for the Admiralty. And one of the things they sent him to do, because the chronometer had gotten to a reasonable level, sent him out to Tahiti to watch the transit of Venus across the sun, while at other places in the world also they were using the same timepieces, synchronizing to determine when Venus would go in front of the sun and when it got to the edge of the disk, and they counted the time frame. And from these various bases around the world, the idea was that that would give them a triangulation to not only determine accurately the distance to the sun, but also the size of the sun. So these pieces of information, these scientific pieces of information, weren't known. They had a pretty good idea, because by then, you know, Copernicus and all those guys had been reasonably well accepted now, and there was no problem with, you know, the Earth going around the sun. It was now, how far are we? What size is the sun? We can tell from the color of it what sorts of temperatures we're dealing with, because light gave temperature away. So this is this period at the end of the 1700s where science was really looking into the world. So one of the reasons Australia got discovered was because Cook was sent down to watch the transit of Venus, do the timing. He was a really accurate guy. He could do this stuff, so he was trusted. And when he'd finished delivering the scientists and doing the experiments that were required, that information was returned back to England. But he was given a notice, by a letter from the Admiralty that said, when you come back, don't come back the way you normally do. What we want you to do is sail directly east and see what you run into. Directly west and see what you run into, which is what happens. So he runs into New Zealand, he runs into in the east coast of Australia, starts to map some of that for us, and so he sails up and around, and then they go, right, okay, you've come back, successful experiment, scientific experiment done, how about you go back and see what you can find out about the Pacific down that region. So he goes, does a couple more journeys, and the rest is history, and we're here because of those journeys, or at least the British population is here because of those journeys. Some might say that was a bad thing for the indigenous, but that's, you know, that's the way it is, I suppose. Anyway, so why is this important to aviation? Because you are actually going to need to navigate on a similar fashion to the way in which you do on water. What's the third, now we're into a fourth thing. What's the fourth problem you have when you are in the air? Altitude. When you're on water, you're on a flat surface, and you can pretty much determine exactly where you are as relation to the flat surface. But where, sea level. But when you're in the air, it's pretty important to know how far up you are, particularly if if your vision's not very good, like at night time or it's cloudy or something like that, because if you don't know what's behind you in mountains and things like this, you can have a few problems. So let's just get rid of a couple of this picture for a moment and think about some of the important things. Two things I've already mentioned before in the previous class was that really navigation is vectoring. If you know the things that you need to know, like either, let's say you know you're heading, what happened to my pen? Right. You might be heading in that direction, but you find out from the currents that are going, you don't actually finish up there, you might finish up over here, because the currents will push you as you were sailing. I'm back to sailing now, I should have mentioned that, back in the water. And so vectoring is easy to see. And in fact, when you start planning a trip on a map as a navigator, you start drawing lines towards the directions you want to go. And you start correcting those courses, those course corrections, as you start to find out from the information you know about the speed you're traveling at, the position of the sun, and the time of the day. And then you say, oh, well, I'm not where I thought I would be. Well, what would be the thing that made a difference? Probably the currents. So you have to keep checking these things. But it's just still vectoring. And navigation in the air is still just vectoring. But you need to know those other things. Now, here's a puzzle. When you're in the sea, they invent, what? Okay, we're on land. We want to know how fast we're going. It's pretty easy. We just measure the distance that we've traveled and the time it took. And that's pretty accurate because the distance is distance. Now on the ocean, they had that trick with the knots, yes. Not absolutely 100% reliable because it doesn't take into account a number of things. Like it's assuming the rate of pull on the water is exactly the same, and that there's not necessarily anything happening other than that's not dragging to the left or to the right. So you're not getting a vectorizing taking place. So it's reasonably accurate. It'll give you a good idea. Better would be if you could somehow know exactly what distance you've traveled. How can you do that? Again, you check against where you are on the map by latitude and longitude on your maps and what time of day it is. So you over a time. Navigation in those days was a series of checking and rechecking positions relative to other things on the map, and then working out how is my knots going. Yes, now, okay, I seem to be traveling a lot slower than what I'm reading. I'm not traveling the distance, and that might be because I'm into a forward current, or I'm arriving in places faster than I thought I was, because I shouldn't have done that because I wasn't supposed to be traveling that fast. And that could be because I've got something pushing me behind. And you make all these adjustments. That's navigation. Okay, so on ground, in a car, your wheels are going around. You attach a reader to the wheel, so every time one circumference of the wheel goes around, you know the distance you've travelled because of the circumference. Easy. Can calculate speed. We knew that from what we looked at when we were looking at transportation. Easy to do, pretty much. How do you do it in the air? You can't drag something behind you because that's just going to disturb everything, and then pull it back in again. So it's not like water. You could try that, but then you're increasing the drag on the aircraft, which is really not what you want to do. So you're not going to throw something out the back. There's no wheel running on the ground, so you can't get it to come out that way. How are you going to know how fast you're going? Tricky. Not easy to do, but there is a way. How do you know how high up you are? Okay, pressure. Tell me again about what you understand pressure to be.
The pressure is greater lower the lower altitude you are due to the density of air.
Density of air? All right, it's density of air, yes, but when you look at, say, the surface of the Earth and then start going up, the column of air that's directly above you does two things. It spreads out, which increases the density or decreases the density, but it also has less air per unit volume above it. So if you're down here at what we call 1 atmosphere, right? Just 1 atmosphere. It's a barometric pressure, and it's usually registered on something like a tube of mercury, that you can measure the way in which the mercury balances on a tube that's got a vacuum at one end and another. So that's barometric pressure. Where have you seen or hear about that when you look at a weather report, for example? What are the lines on the map? Isobars. Isobars. Iso, same, bar at barometric pressure. So they're measured in kilopascals now, right? So it's just the measurement we use because of the metric system. But basically, that's just to show you what the ground air is doing, whether it's low or high pressure. And that's usually an indication of what direction the weather is coming from, or the wind, whether it's a hot day or a cold air mass. But as you go up, the weight of air above you. Now, I gave you that little question to do for homework, which the young lass at Mamre sent me. I'll come back to that in a minute, but that one was the one where it had the dam, and it had a hole in the dam at a height, and it asked you to work out what the force was coming out of the water, or rather the pressure. And it's not as straightforward as you think. Don't need to tell me what it is now, but I'll show you another solution, or something that's just logical that will work for you. All right, got your tower that we've looked at all the time, water tower. Think this one through. If I put a hole in the water tower at this point, and at this point, and at this point, in your mind's eye, what's the water going to look like it's doing when it comes out? The faster at the bottom one, or yeah, it's faster and it will have more force, won't it? So you would expect logically the water to fly out of that one. The one up here will have some force to it, but it won't come out as fast. Right, so the trajectory as it falls into gravity, and this one here, the least of the lot. That has to do with thinking in terms of what is the pressure available from the mass of water above the point. All right. Now that's one of the secrets to why that question had a distance here. But you first have to work out something else before you can do that. All right. So back to pressure here and air pressure. As you go up, the air pressure goes down. So what I need to know is a starting datum point. So I get my barometer, my system of measuring, and that could be using something as simple as mercury in a tube, or it could be a diaphragm in a vacuum. So that have you put a water bottle in the car in the daytime, right? And as it heats up, or the car heats up, the water vapor will slowly but surely come out of the steam area, will come out of even though it's got a tight lid on it, it'll still leak out, right? And then you get into the car later and you find that it's crushed. The bottle has shrunk, right? Because now you have a higher pressure on the outside than you have on the inside. You could use that diaphragm type arrangement to tell you when you are either high or low in terms of the pressure surrounding you. If the container is being pushed in, then the pressure on the outside is higher. If the container is expanding, then the pressure on the inside is higher. So not only can you use just a mercury in a column, you can also use a diaphragm or a balloon to do this. If you know what the balloon is set to, what the base level is. So you set it to 1 atmosphere. And when you go up, as you keep this comparative point staying the same, as the pressure goes down, then the container you have, which has got 1 atmosphere in it, expands. As it expands, you can register that expansion on a dial. That dial in an aircraft is an altimeter. Altitude meter, altimeter, altitude meter. And it's basically on pressure. Just the difference is in pressure. But it relies on you setting it at ground level and knowing what ground level is. Where you can make mistakes with this is if your airport that you're leaving from is an elevated airport. So you have to know the height of your position, particularly if you want to get this right. Mostly time, you said 1 atmosphere is considered what the general air pressure is at sea level. But there's not too many airports that are at sea level. When they had seaplanes and landing on sea, they're perfect. There's your airport, it's the sea level. Most of the airports are somewhere else. So you have to set it to the airport. Now, how about, so that's pretty straightforward. Finding altitude is just a measure of air pressure as you go up the column of air. What about speed? How are we going to do that? We stick our hand out the window and feel how strong the wind is like we're doing in a car, you know? Yeah. Well, you know, it's not unlike that. Seriously, it's not unlike that. It's a little bit more technical than just sticking your hand out the window. But what does your hand tell you when you put your hand out the window? There's force on you. Yeah. So there's wind going past. Air is traveling past the outside of the aircraft. Okay, now, what do we know about air pressure when you are going faster? Column of air, faster. What does Boolean's principle? As you speed up the column of air, the pressure goes down. Lift comes from that. That's the whole process. We want lift, so we want to speed up the air going over the top of the wing. Okay, what if I could tell what the speed of the air is inside the aircraft compared to the speed of the air outside the aircraft? Now, speed of the air inside the aircraft sounds like a nonsense because the air is not moving inside the aircraft, surely. Pardon? It's relative, yes. The aircraft is carrying a package of air in which you are sitting, and surrounding you is a containment to stop your hair being blown away and messing it up, so you don't open the windows in an aircraft, particularly at a very high altitude. Not a good thing. But if you can trap a stagnant air, which means an air that isn't doing anything, it will have a relative pressure. Now that relative pressure is going to be based on the altitude. So now you've got an altimeter that can tell you where your pressure is and what height you are. Now you've got that, you've got a stagnant pressure at a certain altitude. When you stick a little tube out the window, it's called a pitot tube, and you face it forward so that you have air pressure hitting the little pitot tube, the difference between the air pressure resulting from the moving column of air and the air pressure of the stagnant air can be used to calculate speed. Because if you know, as your air column is going faster, it will have lower pressure. And you can even calculate it so accurately that you can get a pretty good idea of how fast you're going. All right, now, those methods have been the main methods for telling us where we are in the air at any time for maybe the first 70 years of aviation. We don't do that anymore. We do still use both of those controls. They're still in the planes, you still use them. Some planes still have the pitot tubes. The pitot tubes had issues though. They had to be reasonably fine so that you could get a good reading. So they had to be reasonably small holes. Small holes block up. One of the problems is you start flying at high altitude, you get colder. And if you have any moisture around, it'll ice up. And if you get it iced up, it blocks, you don't know how fast you're going. That gives you bad readings, and that's not a good thing. Something else they found during the Second World War, particularly when they flew in New Guinea and places like that, is that insects like to go and live in these little holes. And so sometimes they'd be going flying along and they've got no speed registration. They're going, what is it all about? And they get back and they go to these tubes and they clean them out and there's a wasp nest in there or something like that.
That'll do it.
Yeah, that'll do it. So if you don't have that thing clean all the time. So there were some issues with it, but it was pretty good method and it's pretty smart when you think it through. So you use your altitude, or you use your pressure difference between ground level and where you are to determine your altitude, and then you take the pressure at altitude and compare it to the pressure of the wind going past outside to get your speed. Not the wind, the air going past outside. Right? Pretty clever. All right. What do we use today? Well, there's two ways of determining. One is your altitude can be determined by firing something at the ground and waiting for it to come back. What do you think that might be? Sound wave, or it could be light, you could use a laser, or a radar beam. So any form of electromagnetic radiation that can be generated easily can be fired down and wait for the return signal, and you read it and you halve the time and you know your height. Right? And that's pretty cool because that can be dynamic. What that means is that as you go over mountains, it can read those mountains and give you a really good idea of the distance between things as well. So you can keep a certain height above it. A lot of fighter planes in the Vietnam War, for example, the fighter planes relied on ground-hugging radar or terrain-covering radar, so they could get right down low and they'd fire a beam in front of them, and the beam would give them an indication when a big hill was coming up or a tree was coming up, and it'd actually take over from the pilot and lift the aircraft. And the F-111 fighter bomber had this system in it, a few other jets as well, so you could ground terrain hugging radar. The pilot would be assisted in knowing exactly where he was above the ground. They do that so that they could fly underneath the radar beams that were used to pick up the aircraft coming in to an area. So it was a countermeasure, and then they countermeasure that as well. Okay, radar. What else? You're using it all the time in a car. I mean, it's not like it's a trick or anything. It's not a trick question. It's something that everybody uses all the time now. GPS, yeah. Global positioning systems. Now, how does a global positioning system work? Just magic.
Yeah.
Satellites. Okay, what do the satellites do?
They triangulate your position.
How?
Multiple satellites picking up your signal.
No, it's not multiple satellites picking up your signal. Okay, what happened when they first started sending up satellites was they realized that even the very first one, which was the Sputnik, just that you could send a pulse out, and the pulse doesn't take very much to generate. So you can have this thing sending out a radar pulse. Now, a pulse means it can be timed. So if you've got a satellite, any satellite you send up these days has to do this. So they send them up. They've got other jobs. They might be, microwaving information up for television stations or linking phones around the world. But whilst they're doing that, it doesn't take much extra to carry a little clock with you. And a clock that is set to a universal time that everybody agrees on is going to be 0. Greenwich used to be the place that we took time from and still is on our clocks and stuff. So the day still counts from 0. Greenwich Mean Time is considered when, the days, well, actually the date line is the opposite because, that's where the sun is on the opposite side. So there's a date line going through the middle of the Pacific and around some islands. When you have a look at it, it's really weird. So that some islands got missed. So there's an island here that's actually Wednesday and the next island underneath is still Tuesday. and they're only 2 feet away from each other because it went zigzag around. It's a bit strange, but that's, you know, geography and countries and people who wanted to do things that way. So that was the old one. So now they've got this universal clock that's on all of the satellites. Okay, so now you've got your little GPS thing, and this pulse is coming out from all these things, lots and lots of them, all of them are doing it. Your GPS simply goes and just looks at around and picks up the time from all the satellites. Now, a satellite will give you an indication of who it is, like where it is, what type of satellite, and what time it is on that satellite. Now, remember, the pings are all leaving at exactly the same time. All right, so satellite number 1, satellite number 2, satellite number 3, here's the Earth. There's a ping coming out. That ping is travelling out as an electromagnetic ray at the speed of light, all at the same time. So we are down here with our GPS system. This guy's time arrives first because I am closer to that guy. This guy comes in second because he's the next distance, and this one comes in third. Now with 3 I can get a triangulation as long as I assume my height hasn't changed, right? So that I'm on the bottom of the Earth, or at least on the surface of the Earth. So that's pretty reasonable, but it's more accurate if I can get more than that. So most GPSs want you to have at least 5 to 8 satellites. And all it's doing is working out from the delay on the time signal how far away each one of those are, and then it says, oh, well, if that's that far away and that's that far, it draws the circles down, you must be here. That's all it is. So the 4th or 5th satellite might be one that gives you your position in terms of height. So you can tell in an aircraft how high you are off the ground. Right. So you need more than 3 if you want to include one of them to give you a height registration. And it relies simply on everybody knowing the time and what time it is. Time became a really important thing, you see. Having a clock could tell you how far east or west you'd gone. Now we use time to tell us where we are relative to the satellites. And because it's really cheap and easy to do, we can all have a GPS for 200 bucks, put it in your car, and the accuracy's down to 5 meters. Probably get a reasonable idea of your speed as well, although I've been told that the police do not think that you can argue your way out of a speeding fine because the GPS told you you were going at the right speed. All right, they won't rely on that. The accuracy still isn't. My understanding is that it's radar is the best, GPS is not too far behind, but because wheels change in size depending upon how much air is in them or what wheels you put on your car, your speedo is probably the least accurate, and because it's the least accurate, most are designed deliberately to read less than what you are, more than what you're really doing, so that you're always on the safe side of the speedo. But don't trust it. All right, that's not something I'd argue with the police officer who's just booked you for doing 110. But my radar says, mine says, you know, like, that I'm not doing that. Set the GPS to 110 and you get booked anyway. All right. Okay, so there are some key things, and I think we're probably going to need to stop with the time thing so you can go get your reports. All right. Now all of that stuff is in those texts. Have a look at it. The 2 things we're looking at there is altimeters and using the pitot tube system to give you airspeed indication. Airspeed indication. What's another way that a pilot might just be able to work out where he is? Look out the window. So should you override what you see in front of you because the computer says it's this? No. If you want to know why that's not a good idea, look up the accident about the Air New Zealand flight into Mount Erebus. The pilots were actually looking out the window and saying to themselves, there's a mountain in front of us. It's on the record of the flight recording. But they looked at their instruments and the instruments said that they were somewhere else, and they listened or paid more attention to the instruments than what their own eyes were telling them. They got trained out of paying attention. Anyway, Mount Erebus, the Air New Zealand flight. Anyway, yes, look out the window. It's worthwhile knowing.